Bismillahirrahmanirrahim. As a symbol for the variable of interest, we have used phi. But for stress analysis problems, this phi stands for the displacement components. For example, the components u for 1D problem, u and v for 2D problems, and u, p, and w for 3D problems. Because displacement is a vector and it has components. Now, when we talk about 1D problems, u will then take the form ni, nj, ui, u. These are the nodal displacements. Now there are two nodes I and j, and each node has just one degree of freedom. When it comes to 2D problems, now we have the corresponding diagram would be something like this. 3 nodes now. We have an I node, we have a j node, we have a k node. So here we only need one coordinate, and that is x. For a 2D stress analysis problem, we have x and y coordinates. This means that our displacement components are ui, vi, uj, vj, and uk, vk. So there are 6 components. This means that we have to now use phi for u as well as v. The same shape function will be valid for both. So what this means is, if you write in longhand ni ui plus nj uj plus nk uk, I simply replaced phi by u here, but there is a variable v also, because any point inside this element and on the nodes will have a u displacement as well as a v displacement. Shape function will be the same, using the same simplex formulation, nj vj plus nk vk, or in vector form we can write it like this: uv ni nj 0 nk 0 ni 0 nj 0 nk, and here we have ui vi uj vj uk vk. We have used zeros at the appropriate places because this u has nothing to do with the nodal displacement vi, vj, vk. Similarly, v has nothing to do with the nodal displacement ui, uj, uk. Now here, this u is basically, you can say that this is a vector because it has 2 components, and this vector is 2 into 1. Here we have the size of this vector is 6 into 1 because we have 6 components. So this n matrix, this is a matrix of size 2 into 6. And we can call this as u, general displacement vector at any point. It is valid at any point. This is n, and this is vector for the nodal displacements. Now, corresponding to this, for 1D problem, you can just write u is equal to n. This is nodal displacement on the right hand side, but on the left hand side, this is not a vector. This is just a one component, because for these problems, only valid component of displacement is. Now, when it comes to 3D problems in stress analysis, now we have nodes, the corners, the I, J, K, L. In this case, we would need x, y, and z 3 coordinates to define this. because the displacements, any node will have three components of displacement. This is the 3D case. Now, replacing phi for a 3D simplex element with u, v, and w, we'll have to write it like this: u is equal to ni ui plus nj uj plus nk uk plus nl ul. And here we mean that this is ui, uj, uk, and ul. Similarly, there will be vi, vj, vk, and vl, and also there will be wi, wj, wk, and wl, which means that we should also have the expression v equal to the same shape function because it's the same element, this time vi plus nj vj nk vk plus nl vl, and similarly w is equal to ni wi plus nj wj plus nk wk plus nl wl. We can write it again in metric notation like this. It is u v w. This is the displacement vector. This is given by again the n matrix, and this time we have on the right hand side the nodal displacement vector will have 12 elements: ui, vi, wi, uj, vj, wj, uk, vk, wk, ul, vl, and wl. You have these 12 components because there are 4 nodes and each node has 3 degrees of freedom. So this is 12 into 1, this one is 3 into 1, so this n matrix has to be 3 into 12. Now, recognizing from the above 3 expressions that u has nothing to do with v's and w's and so on, ni 0 0, nj 0 0, nk 0 0, nl 0 0. Now in v, this will shift to the right, so ni 0 0, nj 0 0, nk 0 0, nl 0. For w, this is 0 0 ni, 0 0 nj, 0 0 nk, 0 0 nl. Now this expression is equivalent to the above 3 equations. Now, a further thing to consider when we are dealing with stress analysis problems, that is, we are dealing with vectors, is that there is an alternate notation for vector quantities. And the reason being that this u, v, and w is all right as far as we are doing calculations by hand. But as far as the computer is concerned, it doesn't differentiate between u, v, or w. These are all simply degrees of freedom for the as far as the computer is concerned. So what we do is, instead of using u, y, vi, uj, vj, we just use u's. Now, when it comes to 1D problems, this doesn't pose any issue because let's take any element. Let's say an element number 5, for example, in any problem. Node is 4 and node number is 5 here. Now, the degrees of freedom associated with these node 4 and node 5 is U4 and U5 simply. Because in 1D systems, there is just one degree of freedom of interest, and that is U. There is one-to-one correspondence between the node number and the degree of freedom. Node number 4, degree of freedom number 4, that's one, U4. Node number 5, degree of freedom number 5, U5. Very simple in 1D problems. Now, problem starts when we deal with 2D and 3D problem. For example, consider this 2D element. Let's call this I node, this is J, and this is K. And I node for this element number 7, for example, doesn't matter, is node number 4, J node is node number 6, and K node is node number 10. Now the issue is here there's no one-to-one correspondence between the node number and the system degree of freedom. That is because we call that, in this case, there'll be a U4 and a V4, U6 and a V6, U10 and U10 here. In the original scheme, this is simply U4, V4, U6, V6, U10, V10. This is the displacement vector for this element according to the original notation. Now, what about the new notation? Before node number 4, which is the I node here, there are 3 nodes. Each node has 2 degrees of freedom. So 6 degrees of freedom have already been occupied, or they will be occupied if the element containing those degrees of freedom comes subsequent to this element. So the first 6 degrees of freedom are already booked. When we come to node number 4, the available degree of freedom is U7 and U8. Just to think, in the new notation, this is U7 and this is U8 because we are not going to use V and W now. When it comes to node number 6 here, according to the old notation, U6, V6, very simple. But according to the new notation, node number 6, 5 nodes are already gone, accounting for 10 degrees of freedom. So node 6 available degrees of freedom are 11 and 12. So this is U11 and U12. Similarly for node 10, the available degree of freedom will be 19 and 20, because the first 9 nodes will already have accounted for the first 18 degrees of freedom, because this is a 2 degree of freedom system. Each node has 2 degrees of freedom. So here we have U19 and U20. So this is how the computer deals with these degrees of freedom. Numbering. It doesn't bother with U, V, and W. Now, there's a formula that gives us these degrees of freedom according to the alternate notation without having to count the number of occupied degrees of freedom in the system. And that is nodes I, J, and K occupy degrees of freedom 2i minus 1, 2i, 2j minus 1, 2j, 2k minus 1, 2k. Let's check one of these. For example, let's check this U6 and V6. Now this is node j for this element. So 2j minus 1 and 2j. 2j minus 1 gives you 2 multiplied by 6 minus 1, 11, which is the case here. And 2j will give us 12. So this is the shorthand formula for finding out what places a certain node occupies in the global displacement vector. Because recall that all these individual elements will combine at the stage of assembly in one global matrix, and no two nodes can occupy the same space there. We have to have distinct places for every node. Now, when it comes to 3D problems, the situation is similar. For 3D problem, there are first of all 4 nodes. Every node has 3 degrees of freedom. So in this case, by the same thinking, each node will occupy 3 spaces, and those spaces in the global scheme will be node I, j, and k. For node I, it will be 3i minus 2, 3i minus 1, and 3i, 3j minus 2, 3j minus 1, and 3j, and 3k minus 2, 3k minus 1, and 3k. Let's take an example. It's node number 2, which is node I for a certain element. Now, according to the original notation, the displacement components for this node are u2, v2, and w2. It's just about one node here. But what do these displacement components become in the alternate notation? Here we don't use v and w's. We read it off the first line, 3i minus 2, 6 minus 2, 4, u4, then 3i minus 1, u5, and 3i, u6. Now, let's see whether it makes sense or not. This is node number 2. There is node number 1 before this, or it could come after this, depending on the numbering scheme. But it will come sooner or later. So that node number 1 will account for u1, u2, and u3. They are not available, those three. When it comes to node 2, the space available is u4, u5, u6, and it will take space. And then you go on to node 3, node 4, node 5, and so on. Thank you.